In this lab, we're going to look at Ohm's law. Now let's consider a very basic circuit. So here I have a battery, which is a source of voltage, which we'll represent by the letter V here. And here I've got a light bulb. And so what's going to happen when I hook the light bulb up to the battery? What we're going to have is we're going to have current flowing through this circuit. And I've represented the current in green. And usually current is represented by the letter I. Why it's represented by the letter I don't know, but it just is. It just always has been. So this is voltage and current. And then, of course, I have this light bulb up here, and this light bulb is a source of resistance. Now, we've talked about resistance in the lectures, so we know that this is resistance. And it's usually represented by the letter R. Now, current, let's talk about units for just a minute. Current generally has units of amperes, or they call it amps. Voltage has units of volts. And resistance has units of ohms. And that's represented by the capital Greek letter omega, which looks kind of like that. So if you ever see that symbol in an electrical circuit, that's telling you that you're talking about, a resistance. Now, what we're talking about in this lab is what's called Ohm's law. And Ohm's law relates these things together. If I increase the voltage, what happens to the current? If I change the resistance, what happens to the voltage? What happens to the current? These things are all related to one another, and they're related to one another through Ohm's law. And what Ohm's law says is that the voltage is equal to the current times the resistance. This is the equation that we're going to look at dealing with in this lab. Now, there is one other formula that we're going to use, and I just want to remind you of it, and that's the formula for power. Now, if you remember, power is energy divided by time, or work divided by time. And so here we have the battery is doing work on these charges, the current, to push the charges around the wire. That's what current is. It's the flow of charge around the wire. And so we're going to be looking at the battery is using up work. That's why batteries eventually run out. They're doing work. They're using up energy to push the currents around the circuit. And then the light bulb is glowing. It's heating up hot enough to glow. That little filament actually glows. And so it's giving off light. And so the battery is where that energy comes from. And it's being delivered to the light bulb. And so we can talk about the rate at which the light bulb is getting energy, or the rate at which it's using up energy. And that's the power. And in an electrical circuit, the power is equal to the current times the voltage. P is equal to IV. And I actually have a mnemonic to help you remember this formula. You'll never forget it. Here's the mnemonic to help you remember this formula. You will get quite a shock if someone pees in your IV. If you're in the hospital, you don't want that to happen. It would be really bad. All right, you can stop groaning. I know that's really terrible, but let's go on. In this lab, we're going to use some online simulations, and we're going to look specifically at Ohm's law, which is this guy here, V is equal to IR. And in the simulation, you have a battery here, which is a source of resistance. And so I've got a 1.5 volt battery and a half a volt battery that gives me a total of 2 volts. And you can see I've dialed in 2 volts here with this slider. And then I've got my resistance is dialed in at 89 ohms. And I can see the current is read out right here. Now, it's really nice, this simulation that you're going to be using. With your mouse, you can grab this slider and pull it up and change the voltage value. You can grab this slider and change the resistance value. And we're going to see how changing the voltage and how changing the resistance affects the current. And that is the purpose of this lab. And so we're also going to show how we could actually measure this in a lab and with real circuit elements. And I'm going to have you use Excel to make a graph, and we'll see that the graph will verify this relationship as true. So there'll be a Word document that is in the module which gives you instructions, and the instructions will tell you to load up the simulator, and I'll put a link to the simulator in the module as well. And you'll just go through the Word document and you will be able to adjust the parameters and dial in a certain amount of voltage, dial in different amounts of resistance, and then you'll be able to see what the resulting current is. And we're going to have you do that and record the results, and then it'll be like the worksheet style where you can just fill in the answers like we've been doing in the past, and then you'll be able to take your quiz and answer questions about it. In the next part of the lab, we're going to look at series and parallel connections of resistors. Now here I've drawn a typical connection of two resistors connected in series. And so what I have is I have a battery, and then there's a wire connecting to the resistor, the first resistor, and that resistor could be a light bulb, it could be some other circuit element that is providing resistance to the circuit. It doesn't really matter, it's just something that is resisting the flow of current. And so I have resistance R1, and it's going to have so many ohms, and then connected in a straight line to it I have R2, which is a second resistor. It could have a different number of ohms, it could have the same number of ohms, it doesn't matter. And then the wires go back to the battery, and that makes a complete circuit. Now the thing that makes a series circuit is the fact that the current can't split. If this is the current I traveling through this circuit, it has to go through every resistor because there's nowhere else for the current to go. And so when the current makes a complete path from the start of the battery back to the battery, every bit of the current is going through both resistors. And this will make a little bit more sense when I show you the parallel configuration in a moment. But before I do that, I want to point out that when you have a series connection, the two resistors added together like this, they behave like a single resistor with the total resistance being their sum. That is, the total resistance is equal to the resistance of the first one plus the resistance of the second one. And that could be 20 ohms plus 40 ohms or 10 ohms plus 10 ohms. It doesn't matter. However many ohms each resistor has, you have a equivalent resistance that's just adding them up. In other words, if each of these resistors were 20 ohms and I connected them to a particular battery, there's a certain amount of current that's going to flow. Just like we saw with the previous slides with the Ohm's law. If I change the voltage and change the resistance, I'm going to change how much current flows. Right? I put two resistors here, I'm going to get a certain amount of current. Now, if I take these two resistors away and put a single resistor RT, so if each of these were 10, I could replace them with a single 20. 10 plus 10 gives me 20. It doesn't matter, they just add up to give you the total. And so if I replace these two resistors with a single resistor that gives me the total, then what's going to happen is that the current is going to be the same. In other words, the current drawn by these two resistors together is equal to the total current drawn by the total resistance of the single total RT. Now let's look at a parallel connection. So here I have two resistors that are connected in what we call parallel. And you can see the resistors are parallel to each other. That's why we call it that. But the main thing that makes the resistors in parallel is the fact that the current splits. And so if I have my current I coming out of the battery, when it gets to this spot here, some of the current is going to go that way, and some of the current is going to go that way. And so this might be I1, and this might be I2, and then they're going to come back together and rejoin, and guess what? You'll get I together when they rejoin. And so the current splits when you have the resistors connected in parallel. And the thing is, if one of these resistors is bigger, it's going to get less current because it's resisting the current more. So if this is an easy resistor for current to go through, and this is a hard resistor for current to go through, more current's going to go through the lower resistance, the easier one. So for example, if these were two light bulbs, and one of them had a low resistance, let's say R1 had a low resistance and R2 had a high resistance, which light bulb do you think would be brighter? The high resistance one or the low resistance one? It's maybe a little bit unintuitive, but actually the lower resistance light bulb would be brighter. Why is that? Because the lower resistance light bulb is going to be getting more current, and so it would be brighter. Now, incidentally, the formula for replacing these two resistors with a single equivalent resistor, what does that mean? That means one resistor that's going to cause the battery to put out the same amount of current. We find that the total resistance, RT, works out to be R1 plus R2 divided by R1 times R2. And if you have more resistors than just two, the formula gets way more complicated, and there's a simpler way to do a lot of algebra, but I'm not going to make you guys worry about that. But I just want you to understand that the total resistance is different if you have the resistors be in series or if you have them be in parallel. Now, for the second part of the lab, we're going to do another simulation online, and this one involves series and parallel connections of circuits. And here you can see I've got two light bulbs, and they are connected in a series connection. So you can imagine the current's going to come out of the batteries. It's going to go through this resistor, this light bulb, and then it's going to go through the second one, and then it's going to come back to the battery. And that's the complete path of the circuit. And you can see that these are therefore connected in series because the current, it goes through one and then it has to go to the other. There's no fork, there's no split, there's nowhere else for the current to go. That means these have to be in series. Now you can see that down below there's a button, 1 ohm, that's the two values, and I've selected here the button to make it 1 ohm and 2 ohms. And so I've got 1 ohm here and 2 ohms there. And I've checked the calculation button, and so that tells me what the power is. Remember, P is equal to I times V, or V times I. This is the voltage, this is the current, this is the voltage, this is the current. And so we can see that you get different values and different amounts of power having different resistances. And so you'll be able to look at these two configurations and answer questions about the power and the current and the voltage going through each light bulb. And so you'll be able to check here to make it 1 ohm and 1 ohm, and then you'll be able to check here to make it 1 ohm and 2 ohms. And then if you take your mouse in the simulation and you grab this light bulb and you drag it down, so grab the 2 and start to drag it down, it looks like it starts to rotate, and then it will transform, and it transforms into a parallel configuration. So you can see if the current comes out of the battery, it's going to get to this point here and it's going to fork, and some of the current's going to go through this top light bulb and some of the current will go through the bottom light bulb. And so if the current splits, you know the connections are in parallel, and you can actually see these light bulbs are parallel to one another. That's why they call it that. And so then the current's going to come back together at this spot and then go back to the battery. Now, again, you can see down here I can make both resistors, both light bulbs be 1 ohm, or I can have one be 1 and the other one be 2. If I check this calculation button, it'll tell me what the power, the voltage, and the current through each bulb are. And I can use that to answer some of the questions in the worksheet. And just a nice visual thing, remember I told you in this configuration, this guy is going to be brighter. Why is it brighter? Because more current goes through it. More current means that this light bulb is going to heat up and be hotter, and it's going to glow brighter. And so the lower resistance gets more current, and you can actually see visually that this guy is getting more current. And you can actually see that in the series configuration as well, if one light bulb gets more or less current, and you'll be able to answer questions about that in the worksheet. So I think you'll find everything relatively straightforward. Just download the worksheet. I'll put links to both of the simulations in the module, so you can click on the simulation that you're using, print out the worksheet, just fill it out. and then have your worksheet with you when you take the quiz. Now, the only other thing is that I am in the Ohm's Law portion, I am going to have you make a graph, so you are going to need to use Excel. If you're a little bit sketchy on making graphs with Excel, you might want to go back and review the module where we went over how to make graphs and how to do best fit lines with Excel, because you're going to have to do that again. Other than that, I think you'll find everything straightforward. And as always, if you have any questions or problems, just shoot me an email, send me a Canvas message, give me a call, get in touch with me, and I'll do what I can to help. And I will see you guys on the flip side.